Today we're going to look at inverse functions. Let's start off with the definition. If f and g are two functions such that when I do the composition f of g of x, I wind up getting simply x, which would be the identity function. That means that whatever I input, I'm going to get that for an output. And that's for every x in the domain of our function g. And then if I compose g of f of x, it also equals the identity function for every x in the domain of f. Then we say that g is the inverse function of f, and f is also the inverse function of g. And we denote that by f with a little -1 up there. And I don't want you to think of that as f to the negative first power. Don't think of it like a number. 5 to the negative first power means 1 over 5. F -1 does not mean 1 over f. Okay? Not. So it depends on the context of the problem. When you see that little -1, that's referring, if it's a function, that's referring to the inverse function. And it's important to understand that the domain of f must be equal to the range of f inverse and vice versa. Some examples will help. So notationally, we're going to say that that function g is f inverse. We could also say that the inverse of g is equal to f. All right, let's look at some examples. There's different representations for functions that we've learned so far. We learned about a mapping. And a mapping was very easy and visual to see. So if this is the function f, and let me have an arrow here, I can point to things. So this function f maps, for example, 2 over to 3. It maps 5 to 9, -3 to -7, and 1 gets mapped to 1. If I want to create f inverse, what I'm going to do is switch the inputs and the outputs. So what was the domain of f is now going to become the range of f inverse. And what was the range of f is going to become the domain of f inverse. So f inverse, instead of taking, for example, sending 2 to 3, f inverse is going to take 3 and send it to 2. Instead of -3 getting mapped to -7, -7 will get mapped to -3, etc. So I have an easy button to make that happen. And so there you have it in red. This represents f inverse. Notice I'm just basically changing the direction of the arrows. So that's dealing with a mapping. What are some other representations that we've seen? No, not that. Move that down. How about set of ordered pairs? So if I have a set of ordered pairs and I want to create, this is f, I want to create f inverse. So all I have to do is switch my inputs and my outputs. Now for the first ordered pair, 1, 1, when I switch them, it's still 1, 1. So you can't really tell what happened there. But for the next one, -3 went to -7, so that means -7 now gets mapped to -3. 2 goes to 3, so now 3 will go to 2. And 5 goes to 9, so now 9 will go to 5. And that's the worst comma I've ever made. 9, 5. So it's as simple as that. So we're just switching the order of our ordered pairs. What other representations? How about algebraically? What if we have, keep doing that, what if we have equations? So for example, f of x is equal to 2x minus 1. Well, first thing you need to do is, instead of writing function notation, let's write this as y equal 2x minus 1. And if I'm switching inputs and outputs, normally x is the independent variable and y is the dependent variable, because y depends on x. We're going to flip those. So what we're going to do in our equation is replace every y with x and every x with y. So we're switching our inputs and outputs. X becomes y, y becomes x, and now let's solve this for y. I'm going to add 1 to both sides, I'm going to divide by 2, and that's going to be my inverse function. So f inverse of x is going to equal x plus 1 over 2. And that's it. What other forms do we have? Well, how about graphing? let's take the picture of a graph and figure out its inverse. So we have a line. Now if I'm switching inputs and outputs, think of visually if you graph the point 2, 5. For the inverse function, you'll get 5, 2. So 2 goes to 5, now it's going to be 5 goes to 2. So it turns out that every point on your function f is just going to get reflected, if my line shows up, will just get reflected over the y equal x line. And I'll draw that in since it's not here. So if I graph y equal x, not the best, but that's the line y equal x. And if you picture every point reflecting over that, and not disappearing, so I'll write it in red. So that means that this piece is going to wind up going over to there, and this piece is going to go over to here. Notice a couple things. What originally was a y-intercept now becomes an x-intercept. So instead of 0, -1, now it's -1, 0. Any point that's on the line y equal x, like if that was 2, 2, that stays exactly where it's at. Because when you can think of this dashed line as if you had a piece of paper on your desk and you were graphing the blue line with a marker and it was still damp, and then you folded your paper on that dashed line and pressed it together really hard and then opened it back up, where else would show up in blue? Well, this piece here would wind up making a mark on over here, and this piece of the blue original graph would wind up being over here. So let's go back and summarize what we had. So if it was a set of ordered pairs, if it was a mapping rather, to find the inverse, we just switch the direction of the arrows. Sets of ordered pairs, we just flip the order of each of those ordered pairs. Algebraically, we write it as y equals our function, and then we replace every x with a y and y with an x, and solve for y. And graphically, you just reflect your graph over the y equal x line to get your inverse. All right, we mostly focus on the algebraic when we have a function written like this. So here's a function h of x equals 8x cubed plus 2. Let's find the inverse. So what was step 1? We write it as y equals, and then we switch all the x's and y's, so that becomes x equals 8y cubed plus 2. And then we solve for y. So I'm going to subtract 2, divide by 8. That equals y cubed. And then I'm going to need to take the cube root of both sides to solve for y. And I'm going to get the cube root of x minus 2. And then the cube root of 8 is just 2, so I can simplify that. And on the other side we have y. So h inverse of x is going to equal the cube root of x minus 2 all over 2. And that's it. All right, find the inverse of this function. G of x equals the square root of 3x plus 1. You might want to pause, try and do it yourself, and then see how you did. Step 1, we write it as y equals. Then what do? We switch all the x's and y's, and then we solve for y. So I'm going to need to square both sides to get rid of that square root, so I can solve for y. And I'm going to have x squared minus 1 divided by 3 is equal to y. So that tells me that my inverse equals that quadratic. And right away I'm thinking of visually, what does that mean? And I'm starting to have a little bit of a concern. So let's take a look at the graph of this. If I go to y equal and graph the original g of x, that was the square root of 3x plus 1. And then, well, here, let's zoom 6. And we know what a square root graph looks like, and it's been shifted a little bit. -1/3, 0 is the starting point. Now let's go back and graph the red one, and that was x squared minus 1 over 3. And it looks like we have more red than we do blue. What's going on here? Well, let's go back and graph y equal x. And remember, we're reflecting our original blue graph over that black line. Well, we're not going to get all of that stuff in red, are we? We're just going to get about half of it. So what part are we going to get and what are we leaving off? Let's go back here and look at the domain. And this is an important thing to understand. The domain for g of x, I know I have the square root. I can't take the square root of a negative in the real number system. So I know that 3x plus 1 has to be greater than or equal to 0, which would mean x has to be greater than or equal to negative 1/3. That means for the range of my inverse, y is going to have to be greater than or equal to negative 1/3. What about the domain? Well, what's the range of this original function? Let's go back to our graph. If I hit trace, and I type in negative 1 divided by 3, that's where it starts. Notice it has negative 1/3 comma 0. And then as I move along the graph, when x is bigger than negative 1/3, it keeps going up and up and up and up and up. So the range of this blue function is 0 to infinity. So let me write that. This is x greater than or equal to 0. That means the domain of my inverse, oops, I should have written that as y equal, not x equal. And then I just messed it all up. Range, y greater than or equal to 0. That means my domain for the inverse is going to have to be x is greater than or equal to 0. So I'm going to have to add that specification here that x is greater than or equal to 0 for my inverse. Otherwise, I'm getting too much of the graph. And so that's why it's really important not only to just switch your x's and y's, solve for y, and say you're done. You have to look at the original domain and range and see how that ties into restrictions for your inverse with domain and range. If I go back to my calculator, I can trick it a little bit though. I can go to y equal, and for my inverse, let's do the second in parenthesis, jump to the end parenthesis. If I take that expression and I divide it by the logical statement that x has to be greater than, where is that? That's in the test menu. Greater than or equal to 0. So what's going to happen, without getting too deeply into this, is as long as x is greater than or equal to 0, it'll evaluate x squared minus 1 over 3. When x is not greater than or equal to 0, it's going to return a false statement, which essentially tells this to divide by 0, which is undefined. So watch what happens. It just graphs the piece that I want it to graph, starting at 0, negative 1/3, and then continues up. So it's a good reflection of the original function over y equal x. All right, so that's a lot to take in. You might have to go back and rewatch this example to understand it if you didn't quite get all the subtleties of that. What else can we look at? So this inverse that we've been calculating of a function, the inverse itself will be a function only if our original function is 1-to-1. What do we mean by that? A function is 1-to-1 if it passes the horizontal line test. Let's just go right to an example. What if I had y equal x squared? What does the graph look like for that? We know what the graph looks like. Right there. We're going to have a problem because this is not going to pass the horizontal line test. It is a function, so it does pass, let's go with the yellow, it does pass the vertical line test. Any vertical line I draw will only hit this function in one spot, this graph in one spot, so it's a function. It does not pass what we call the horizontal line test. It's hitting it in two points at any given y equal greater than 0. Why does it work that way? Well, for example, let me write a couple of ordered pairs. Let's say we take the point here, 2, 4. What about the point over here, -2, 4? If you think of lists of ordered pairs, we're writing a function this way. It's okay if, draw an arrow, it's okay if the second number repeats. It's still a function, as long as the first number doesn't repeat. As long as if 2 goes to 4, later on down the line, 2 can't go to another number like 17. Then it's not a function. But now when I'm doing my inverse, I'm switching the order of these numbers, right? So now the inverse is going to wind up being 4, 2. And this one's going to be 4, -2. And now I have a problem because now I have 4 being mapped to 2 different values. And so this red inverse that I've created is not a function, although the original one was. So the way to tell if your inverse is going to be a function, to know that if you'll have first numbers repeating, that'll happen if the second numbers repeat in the original. And so in other words, we use this horizontal line test to tell if the inverse of a function will also be a function or not. And so in this case, no, the inverse is not a function. So that's a visual explanation of it. And what would happen if we went ahead and just tried to solve it? We'd have x equals y squared. And then we take the square root of both sides, and we get the absolute value of y equals the square root of x. So therefore, y is equal to plus or minus the square root of x. So now if you pick a value for x to plug in, you get 2 different y values. So obviously it's not a function. Is the inverse f inverse a function? Let's look at this example. So my original, f of -3 is 5, f of 1 is 0, f of 0 is -3, f of 1/2 is 2, f of 4 is 0. That is a function because none of these red numbers repeat and get mapped to a different blue number. But what if I create the inverse? Then I'm switching the order. So then 5 is getting mapped to -3. 0 is going to 1. -3 is going to 0. So far, so good. 2 is going to 1/2. Looks really good. Uh-oh, 0 gets mapped to 4. That's a problem. I have 0 being mapped to 1, and then later it's being mapped to 4. So this inverse is not a function. So what are we looking for? Originally, to figure out if something was a function, we just made sure none of the x numbers repeated. Now, to decide if the inverse is a function, we have to make sure that the y numbers don't repeat. Or in other words, our original function is 1 to 1. All right, 2 more examples. Let's say f of x is 5x plus 3. Find f inverse of -2. Now notice, instead of finding the general inverse, I'm asking to evaluate the inverse at a specific number. So there's 2 ways to do this. First way, which most students would do the first time, is they'd say, okay, let me figure out what the inverse is. Let's write it as y equal 5x plus 3, switch the x's and the y's, and solve for y. Subtract 3, divide by 5. There's my inverse. So f inverse of x, so the general inverse, is going to be x minus 3 over 5. So now I can evaluate f inverse of -2 and just plug it in. So I'm going to get -2 minus 3 over 5, and that gives me -1. So that's one way to do it. Another way to do it, you can think about this visually, is here's my domain, here's my range. And my function f is mapping numbers from the domain to elements of my range. So if I want to know what's f inverse of negative 2, I'm looking to see if negative 2 is over here, what got mapped to negative 2 for my function f? Because the inverse will take negative 2 back to whatever that number is. So thinking of it that way, what you could do is you could take negative 2 equals 5x plus 3 and solve for x. And that'll tell us what that number was. So we subtract 3, we get negative 5, then we divide by 5, and sure enough, we get negative 1, which was the same answer we got this way. So two different ways of looking at it. All right, one last example. Find the composition now of f with its inverse function at 7. How do we do this? Well, we could do what we did before. We could figure out what the f inverse function was, x minus 3 over 5. And so what are we going to do? We're going to do f of f inverse of 7. So we're going to do x minus 3 over 5. We're plugging in 7. That's going to give me 4/5. And then I'm going to plug 4/5 into f right there. And so that's going to give me 5 times 4/5 plus 3. 5's cancel, 4 plus 3 is 7. And then you realize, wait a minute, that's kind of weird. That's what I started with. That's what I finished with. Let's go back to thinking about a mapping. Okay, so here's my function f. I want to do f inverse of 7. So 7 is over here. F inverse is going to take 7 and map it over to something here. We'll call it x. That takes care of this part. I don't know what that x number is. I don't need to figure it out though. I don't really care. Because then I'm going to take f of that. And f of that will take me right back to here. So in effect, these are kind of canceling each other out. They're taking me on a roundabout trip. So I started at 7. F inverse took me over to here, whatever that is. Who cares? But then I'm going to take f of that, which I know will take me right back to where I started. So sometimes thinking a little bit instead of diving in will save you a little bit of time.